Hello everyone, I'm Srikanth, currently working in Marvell's machine learning team as a principal engineer. I'm also the maintainer of DPDK's MLDEV library and test application. And along with that, I also maintain the ML drivers for Marvell's CNXK or Octium platform. In this session, I would like to introduce and discuss about the machine learning capabilities in DPDK. I would be presenting the background for introducing the MLDEV library, its features, followed by a walkthrough of the current MLDEV specification and the future roadmap. I would also briefly talk about the performance observations that we have made using the MLDEV specification. Before we start, I would like to give a brief overview of machine learning usage in networking and then packet processing domains. Before we start discussing about machine learning capabilities in DPDK, I would like to briefly introduce the life cycle of a typical machine learning model. So at the top level, the cycle usually has three different stages. The first one being data preparation, followed by model building and training, and then followed by deployment and monitoring. In the data preparation stage, the acquired data is cleaned to remove any outliers, missing data, or any kind of noise, and then the data is scaled and normalized. This stage also includes labeling and feature extraction. Along with this, the total data that is available is split into two different data sets. One is used for training and one for validation. The second stage is model building, which usually involves choosing the appropriate algorithm, followed by training the model using the training data set and validating the generated model using the test data set. It also includes tuning the hyperparameters for the model, which would enable the model for an optimal performance. The last stage includes deploying the model in production and tracking the accuracy of the prediction. This would help in identifying any retraining requirements or any adjustments that are required to improve the model performance. Now, coming to the scope of DPDK, the scope of DPDK includes only model deployment, specifically model training, which would enable running the model inference operations or predictions on ML accelerated devices. Now, if we observe the recent trends, other than the regular use cases of machine learning in domains like marketing and sales, analytics, customer support, human resources, and others, we are observing an increased interest in using the ML models in domains like networking, cybersecurity, packet processing, etc. And also, we are also observing an increasing trend in use of ML models on edge devices, specifically in radio access networks, and basically covering the 5G and 6G space. These domains that which involve the networking and packet processing typically involve fast processing of live network packet data, and also they require the inference operations being performed with extremely low latencies. The use cases would also involve model deployment in both data centers as well as the edge devices. Majority of the ML inferencing deployments use either an external ML accelerator or an integrated ML accelerator to offload the ML operations. Typically, an external accelerator is a device connected to the host machine through PCI. They have a wide range of capabilities in terms of the ML models or the operators that they support. An integrated accelerator is generally a custom ML accelerator, is vendor specific and are generally integrated into the SoC. The integrated accelerators are designed for a specific type of workloads and can support a very limited set of operators. They are usually power optimized in nature, and since they are integrated into the SoC, they provide a very tight integration with the data path. Now, as we know, DPDK is primarily meant for accelerating the packet processing workloads. Supporting ML in DPDK would enable us to use both the accelerated device types for inference offload operations. Coming to the use cases of ML in networking domain, we are seeing an increase in use of ML in areas like intrusion detection, traffic classification, anomaly detection, endpoint security, malware detection, and various other areas. Use cases for intrusion detection can include one specific model like Lucid, which is a CNN-based model that can be used to detect DDoS attacks. And another use case could be a deep defense, which is based on a bidirectional LSTM, and also uses RMN and CMX for the intrusion detection purpose. Now, this slide shows few other examples for the use cases in traffic classification and anomaly detection. We can see that people have used CNNs, RNNs for both the scenarios for like traffic classification and anomaly detection. I have not covered the use cases specifically for endpoint security and malware detection as part of the slides. In this section, I'll talk about the top-level features of MLDEV library in DPDK. MLDEV library provides a very generic ML device framework to support inference operations. Support is enabled for both physical devices, which are backed by the hardware, and virtual devices, which are backed by the software. The library provides APIs to configure and manage the devices. Along with this, it also supports APIs to run the inference operations and do some pre-processing and post-processing of the input and output data that is used for the inference operations. Now, all the APIs defined by the specifications are implemented by the vendors through platform-specific pole mode drivers. This slide talks about a typical MLDEV flow to run an inference operation using the ML device specification. Now, the flow includes multiple stages. The first stage being device initialization, followed by model initialization, then input data handling, and the actual inference, which includes both enqueuing and dequeuing the inference operations. Post inference, the next stage would be output data handling, and followed by model and device termination. Of these all operations, the device or model initialization and termination can be considered as control path operations, whereas the IO data handling and the inferencing can be considered as the fast path of the data path operations. As said, the API framework supports multiple devices, and each device has configurable queues per device, of course, subject to the hardware capabilities. A two-stage model initialization and termination, along with support to dynamically update the model parameters. The API framework also supports quantization and dequantization of the input and output data that is used for the inference operation. Along with that, the API also provides certain utility APIs to manage the devices and the models that are involved in the inference operations. Now, I will walk you through the MLDEV API specification. In the MLDEV's context, an ML device is any device that is capable of performing inference operations using a pre-trained model. It can be either backed by a physical device, which is based on PCI, or a software device based on the DPDK's virtual device. The device is configurable as per the application's requirements, and it supports multiple queue pairs. The specification provides APIs to start or stop the device and to retrieve the device and debug information. Now, the software-based devices are backed by DPDK's virtual device, and the implementation can be based on runtime frameworks like TVM or Onyx or any other runtime frameworks. They typically use the CPU cores for inference execution, whereas the hardware-based devices are backed by PCI-based ML accelerator devices, and inference operations are offloaded onto the device as per the device specification. The specification provides APIs for device management, enabling or disabling the device, setting up queue pairs, retrieving the device info, and then a couple of APIs for debugging purpose, and then few utility APIs to get information related to the devices. Now, configuring stage typically includes initializing the internal resources for the device, and starting the device would enable the device to accept requests related to model and inferencing from the application. Now, RTML dev info get is an API to fetch the information related to the device, which would typically include, the information would typically include the maximum number of models supported by the device, maximum number of Q pairs supported, maximum number of descriptors for each Q pair, the maximum number of input or outputs that a model can support, and then the number of segments that the device can support for each input or output, and any hardware specific alignment, hardware or software specific alignment requirements that are there for the device. Now, the debug APIs include RTML dev dump and RTML self test. Dev dump is used to dump all the device's hardware or software debug information, and self test is an API that is used to test the health of the device. The device utilities include RTML dev count is a valid device to check whether the device is valid or not, then an API to get the socket information for that device. As we know, inference operations require an ML model to be used. Depending on the device being used, the model can be in a native format or a compiled format. Native formats are used in cases where the device is based on a software runtime like TVM or Onyx. And compiled models are generally used in custom hardware accelerators. Now, the model operations are primarily of two types. One is for enabling the devices, enabling the models, and second is for disabling the models. These two operations are again split into two different stages. For example, if we take these operations for enabling the models, this operation is split into two different stages. The first one being load, and then the second one being start. The load operation is meant for initializing driver resources for the model, and the start would enable the device to accept the inference requests specific to that model. Now, on a hardware-backed device, the start could also involve copying the model data to the hardware. Now, having this two-stage approach for enabling a model or disabling a model would help us to optimally use the limited hardware resources on the device. For example, we can have multiple models to be loaded, but we can start only a limited set of models that for which we want to run the inferences at that point of time. Right? So this would basically limit the use of hardware resources by only the models which are actually being used to run the inference operations. Similarly, disabling a model is also a two-stage process, which involves stop and unload. Stop would release the resources allocated for the model on the hardware device, whereas unload would release all the resources allocated for the model by the driver. Now, a model that is stopped can be started again without reloading the model. Now, MLDEV also supports updating model parameters for a model without downloading. This is provided using the API RTML model params. Now, each model that is loaded is mapped to a specific device and is identified by a model ID. Now, this model ID is unique for a given device. The model ID can be same for different models mapped to different devices. The specification provides APIs to retrieve the model and input-output information of any model that has already been loaded on a device. Model information includes the name of model, version of the model, model ID, the ID of the device to which the model is mapped to, minimum number of batches and maximum number of batches supported by the model, which can be used to run batch mode of inference execution, the number of inputs expected by the model, and the number of outputs given out by the model. The model info also specifies the I/O layout expected for that model. Basically, the I/O layout talks about the expected layout of the input and outputs. Supported types include packed and split. Now, when the layout is packed, all inputs and outputs are expected to be in one contiguous buffer. Whereas in case of split mode, different buffers can be used for each input and output. Now coming to the I/O info includes the number of dimensions, the shape of the tensor, then type of the data, the number of elements, total number of elements, and then the size of each input or output. The next set of APIs that I would like to discuss about are related to data quantization and dequantization. Now, data quantization is basically conversion of data from a higher precision type to a lower precision type. Now, use of this lower precision type of data for inference operations would actually improve the computational performance of the model with the loss of precision, which is usually in an acceptable range. The support in DPDK is for 8, 16, and 32 bits, 16, 32, and 64-bit integer types, and 16, 32-bit floating point types, along with bfloat16. Now, the library also has an optimized implementation, software-based implementation of the conversions, along with an optimized neon intrinsics-based implementation for AR64 architecture. The ML specification provides support for a structure called as RTMLOP, which can be used to handle the inference operations. It is used to specify the model ID to be used for the inference operation, along with the input and output buffers that have to be used for the inference. The RTMLOP also provides support to specify the number of batches for which we want to run the inference for. Along with this information, the RTMLOP also provides support to pass some context information from the enqueue thread to the dequeue thread through a user handle field. The MLOP can be used to retrieve the driver-specific error code and a human-readable error message in case of an error during the inference operation. The RTMLOP is basically managed through a mempool. The ML spec provides APIs to create and free the MLOP pool. We can actually use the generic mempool functions like get input or get bulk input bulk to allocate or free the MLOP handles from the mempool. Now, this allocation, as it is coming from mempool, the allocation is thread safe and is also cache aligned. Now, the APIs that we are talking about are the RTMLOP pool create and then RTMLOP pool. The MLDEV spec provides fastpath APIs to enqueue and dequeue inference operations. The APIs support burst mode of enqueue and dequeue to handle multiple inferences in a single call. There is an option to specify the queue pair to be used for the inference operations. Now, coming to the number of actual ops that are enqueued or dequeued would depend on the free slots available within the queue. The two APIs that we're talking about are the RTML enqueue burst and then the RTML dequeue burst. MLDEV specification supports a generic approach to retrieve the statistics through the XStats APIs. The XStats API supports both device and model stats. Supported stats basically are defined by the driver. Now, usually, like device stats can include the number of inferences enqueued, dequeued, number of inferences failed, errors, and then the number of models loaded. Whereas for the model counters, it can include the number of inferences enqueued specific to that model, and then similarly the inferences dequeued or errors. Additionally, we can also report the fields like latency, throughput, or any other device-specific parameters as part of the model's XStats. I would like to talk briefly about the current status of the implementation of libraries, drivers in the test application. Now, coming to the specification and library, the APIs with library implementation is added as part of the DPDK 23.11 release. Test application is available as DPDK test MLDEV. Now, test application currently covers all features like single or multimodal execution, then queue pair handling, inference validation as well. And it also supports, for example, for inference operations, it supports interleaving and non-interleaving mode of inference operations. Now, coming to the contribution library, it's contributed by Jaren Jacob, Shivashankar, and myself from Marvell. Coming to the drivers that are currently implemented, we have implemented the Marvell PMD implementation. This implementation currently works with both the models that are compiled using Glow compiler framework and also the TVM compiler framework. Now, the driver is also integrated with the TVM runtime. It supports both the PCA-based ML accelerator engine and also the software-based VDEV. The implementation currently supports all the RTML APIs that are defined by the spec. Key contributors for the driver implementation include Anup, Prince, and myself from Marvell. I would like to quickly talk about the performance observations that we have made with the current implementation. As part of testing the library and the driver that we have implemented, we have tried inference operations with various models that are available in the public domain. Now, in this slide, I want to mention the performance of ResNet 50 and 18 models that we have observed. What we have observed is a throughput of 175 or 408 samples per second with ResNet 50 model, based on the quantization type that we have used, and similarly 376 or 865 samples per second for ResNet 18 model, depending on the quantization type that we have used. Now, what I would like to really highlight in this slide is the extra latency that DPDK adds to NQ or DQ the inference operations, which is as low as 1.1 microseconds. I would like to conclude my presentation with the future roadmap that we have planned for DPDK MLDEV specification. In order to enhance the ML device specification and also to tightly integrate the ML device specification with the rest of DPDK specification, we would like to use the RTE MBUF for input and output buffer handling. And we also want to decouple the quantization or dequantization APIs with the model ID and add support for data type conversion APIs. As part of the new data type conversion APIs, we would like to enable support for affine or asymmetric quantization also. Along with this, as an enhancement to the model info, we'd like to add support for the dynamic shape in model info structure. And we would also like to add in specification for ML event adapter library, which would enable integration of the ML devices with the event devices.